300plusacademy.com with yet another probable question in practical physics. Okay, alternative to practical physics. Now in this question displaying on your screen, it talks about a photocell connected to a battery and a milliammeter to measure small current. In this experiment, ultraviolet rays are shown on the photocathode and the resulting photocurrent is measured with milliammeter. The intensity E of the incident rays is adjusted and the corresponding photocurrent I is measured. Okay, as you also see on your screen, it talks about two figures displaying. One is for the intensity of the incident rays, that's figure 3A. It talks about the intensity E of the incident rays shown on the photo cathode, and of course you have a milliammeter to take record of the photocurrent generated as a result of that. So looking at this question, we're told to measure and record the real values of E, that is the incident radiation E, and that's in candela, because you recall that talking about the fundamental quantities and fundamental units of physics, luminous intensity is one of the fundamental quantities we have, and the unit of luminous intensity is in candela. As you can see on figure 3A, we're given a scale which states that 1 centimeter represents 10 candela. Yes, 10 CD, that's 10 candela. Okay, so Roman figure 1, measure and record the real values of the intensity E of the incident radiation. So measuring E1, E2, E3, E4, E5 and E6. Actually, by measurement, E1 is actually 2, but because the scale is saying that 1 centimeter could represent 10 candela, shortened as CD. Okay, so 2 times 10 is going to give us 20 candela. For the second one, the intensity of the incident rays E is actually 3 centimeter, but of course because of our scale we are talking about 3 times 10, and that gives us 30 candela. Then this 4 centimeter gives us 40 candela, 5 centimeter gives us 50 candela, and 6 centimeter gives us 60 candela, and 7.2 centimeter gives us 72 candela. Now let's look at the next question. It says Roman figure 2, read and record the corresponding current I. Now talking about the corresponding current I, measured with a milliammeter, of course in milliampere as well. No scale for that, that's figure 3B as you can see on your screen. Okay, what we have is 0.2 milliampere, 0.61, 1.40, 1.80 and 2.40 milliamperes. That's on Roman figure 2. On Roman figure 3, I was told to evaluate inverse of my current. Yes, inverse of my current, and then inverse of my of the intensity of my incident rays, inverse of I and inverse of E. So inverse of I is going to be 1 divided by 0.25, 1 divided by 0.61.67, 1 divided by 1 divided by 1.40, 0.71 milli per milliamperes, 1 divided by 1.8, 0.56 per milliampere, and 1 divided by 2.40 gives me 0.42 per milliampere. Okay, trying to get the inverse of the intensity, yes. Trying to get the inverse of the intensity of the incident rays E. Okay, 1 divided by 20 is going to give us 0.05 per candela. 1 divided by 30, 0.033 per candela. 1 divided by 40, 0.025 per candela. 1 divided by 50, 0.020 per candela. 1 divided by 60, 0.017 per candela. 1 divided by 72, 0.014 per candela. Okay, Roman figure 4, we were told to tabulate our readings, which we've done already. And for Roman figure 5, we were told to plot a graph of the inverse of the intensity. For Roman figure 5, plots a graph of the inverse of the intensity of the incidence rays in per candela against inverse of the current in per milliampere. So which means this will be on the vertical axis and this will be on the horizontal axis. So to do that, you know you need your ruler. So the first thing to do is to write out your title. You say graph of the inverse of the intensity in per candela against inverse of the current per milliampere. Okay, that's what you have. And of course, irrespective of the figures for my horizontal and vertical axis, okay, what that means is that this is going to be my vertical axis and this is going to be my horizontal axis. Okay, so I just want to draw a straight line first. I want to draw a straight line first. Draw a perfect straight line first. Okay, that I'm able to do. Okay, and then I want to draw for my horizontal axis as well. Okay, that I've been able to accomplish, and I make sure that none of this is actually getting out of my graph. Okay, I'm going to start both from the zero origin. Now the next thing is for me to take a point, is to take my points rather. Okay, the smallest figure here is 0.014 and here it is 0.05. So I'm looking at like 0.01 to 0.05. So normally in this case I'll do like 0.010. You see that? 0.010, 0.020, 0.030, 0.040, 0.050, you know, but that's because of the size of my graph here. When you're plotting on paper for a graph like this, you should be using 1, 2, okay, 1, 2, that's from here to here is 2 centimeter, from here to here is 2 centimeter. So you should be using 4 centimeter to represent 0.010 per candela. You recall that this is my intensity in per candela. Okay. So what I'm saying is this. In this case, for my intensity of my incident rays, e raised to power minus 1 in candela CD raised to power minus 1. My scale is looking like 2 centimeter to represent 0.01 candela. Okay, but if you are using your paper graph, on your paper graph you should be using 4 centimeter, like from here to here, from here to here, 4 centimeter. That's what this would be. Here. So this is 4 centimeter on your graph. 4 centimeter to represent 0.010 per candela, and you will still be right. And that will allow your graph to cover, a greater percentage of your graph book. Okay. For the horizontal axis, that represents inverse of my current in per milliampere. Okay, and what I have there is 0.42 to 5. So I just want to get this down. 1.00, 2.00, 3.00, 4.00, 5.00, and I think with that I'm good to go. So what I want to do now is to pick my point. So I think I'm very much okay with that. So having done that, the next thing to do, okay, let me put down, I have to put down the unit for my horizontal axis. This is 2 centimeter to represent 1 2 centimeter to represent 1 per milliampere. So what I'm going to put here is, okay, my I raised to power minus 1 in per milliampere. 2 centimeter represents 1.00 per milliampere, and I'll be correct. I've been able to get my scale down. So the next thing to do is to try to pick my points. Yes, to pick my points. Now, when the inverse of the intensity is 0.05, the inverse of my current is 5. So that's very easy to spot. Here and here. That's very easy to spot. Okay, and then the next reading is when this is 0.033, 0.030, 0.031, 3 to 3 is somewhere here, 3, and 1.67. This is 1, 1.1, 1.2, 1.3, 1.4, 1.5, 1.6, 1.7, in between. So I'm going to try to look out for that. Okay, I'm able to take that. Okay, and then I have 0.025. This is 0.02, 21, 22, 23, 24, 25. 25 and 1. Okay, this is it, 1. So this is my point here. Okay, that is that 0.020, which is this, and 0.71. Okay, 0.1, 0.2, 0.3, 0.4, 5, 6, 7, somewhere here, and this. So I have it somewhere here. Okay, that ends that. For the fifth serial number, 0.017. This is 0.010, 1, 1, 2, 1, 3, 1, 4, 1, 5, 1, 6, 1, 7. Okay, 1, 7 is somewhere around here, and 0.56, 0.1, 2, 3, 4, 5, 6, somewhere in between. When I trace that up, I have it somewhere around here. Okay, and then to the last serial number, 0.014. 0.014, 1, 1, 1, 2, 1, 3, 1, 4, somewhere around here, 1, 4, and 0.42, 0.1, 2, 3, 4, somewhere around here. So if I trace that up, somewhere here. So I've been able to pick all of my 6 points. So that ends that. So on Roman figure 6, I was told to determine the slope of the graph. Of course, to determine the slope of the graph, I need to try and pick together at least 3 points. And when I look at this, if I start from here, I would only have been able to pick 2. You can see, I would only have been able to pick 2 if I start from here, leaving out this. If I try this, it's not going to go. So the last 4 is what is looking probable for me to at least get a 4-pointer here. So you see that this is going to be able to pick 4. This is going to be able to pick 4. So I want to try that just immediately, and that's it. I've been able to be 0.1, 0.2, 0.3, 0.4. That does it. So I am trying to look for my slope here. So okay, I'm going to stick with something I'm comfortable with, like I always say. Also, graph, you pick your point perfectly well, then your slope normally will comply. The slope is going to present itself once you've done the right thing. You're going to have issues once you've compromised along the line. So this is going to be my change in the inverse of the intensity in per candela, and this is going to be my change in the inverse of the current in per milliampere. Okay, now I want to just pick out those points. Okay, I have this topic here, so I want to pick that out very well. And okay, this does it here. So if I look at it, 0.051, 52, 53, 54, 55, 56, 57, 58, 59, 0.06. So this means 0.059. Okay, and for the horizontal axis, I have my extrapolation somewhere here. 2.1, 0.2, 0.3, 0.4, 0.5, 0.6, 0.7. So that is 2 at 2.70. Okay. And the second one stops somewhere here. That is 0.2. So that once I come here to try to get my slope on question 6, my slope is going to be changed in the inverse of the intensity of the incident rays in per candela divided by change in the inverse of the current in per milliampere. Okay, so what this means is this 0.059 take out 0.010 in per candela, all divided by changing my current here is 2.70. Take out 0.20 in per milliampere. Okay, this is going to give me 0.049 divided by 2.50 divided by 2.50. Okay, this is going to be 1 over candela times milliampere over 1. So that I know that my unit is milliampere per candela. Also written as milliampere per candela. So 0.049 divided by 2.50. 0.049 divided by 2.50. Okay, I have 0.0196. 0.0196, which I can approximate to 0.020 milliampere per candela, and I'll be correct to do that. Yes, I'll be correct to do that. So that is the value of my slope. That ends question 6. Question 7 talks about stating precautions that are necessary to ensure accurate results when performing this experiment. On question VII displaying on your screen, it talks about stating 2 precautions necessary to ensure accurate results when performing this experiment. Of course, if you look at this experiment, you have a battery there and you have a key there. So I'll take from the third one. Sorry. Okay. From the fourth one, once you see a battery and a key, it is always very important to open the keys when readings are not being taken. That is to ensure we don't run down the battery. We open the keys when we are not taking any reading. Okay, we also, of course, it's electricity. You ensure tight and clean terminals. Also, you avoid parallax error when taking your reading from the milliammeter and the meter rule. Also, you must take notes and correct for 0 error on the meter rule. Yes, in measuring, the height of the intensity in figure 3A, and you have to correct 0 error on the ammeter reading as well. And of course, if you look at it, we were told to repeat this experiment 6 times. Why are we repeating the readings? It is for accuracy. So these are the precautions we are to take if we are performing this experiment in the laboratory. And that ends question A. Question B states, differentiate between red light and violet light in terms of, you have to differentiate between B1. We want to differentiate between red light and violet light. Okay, and we are to carry out this differentiation in terms of A, wavelength, otherwise known as lambda, and B, in terms of energy. In terms of energy, okay, we want to differentiate between the red light and the violet light in terms of these two. If you're very conversant with physics, you recall your Roy leaf, red, orange, yellow, blue, indigo, and violet. Okay, now when you look at that, I'd like you to know that this side has the lowest. From the red light, they have the lowest energy. You have the lowest energy, that's the red light. And for your violet, they have the highest energy of the spectrum. They have the highest energy. They have the highest energy for the spectrum. Now, talking about wavelengths, high energy means short wavelength. This has the shortest wavelength. The side, and this side has the longest wavelength. That's talking about the red light, longest wavelength. Okay, so and what I'm being told to do here is to just differentiate between red light in terms of the wavelength and in terms of the energy, and that's just explaining. So how am I going to put that? I'm just going to say, okay, this has a long wavelength and this has a short wavelength. Talking about energy, this has very low energy and this has very high energy. Okay, that differentiates that, and that is B1 for 2 marks. Okay, moving on to B2. Moving on to B2. Moving on to B2, we have a question there. The question reads, a red light has a wavelength of 700 nanometer. Wavelength of 700 nanometer. Okay, what else? Calculate its energy. I was told to do for the energy. Energy is a question here. I was given Planck's constant H. Planck's constant H. Okay, let me put that here. Planck's constant H to be 6.6 times 10 raised to the power minus 34 joule seconds. Okay, and I was also given the speed of light C to be 3 times 10 raised to the power 8 meter per second. I was told to look for the energy here. Of course, what formula am I going to use? Energy here is Planck's constant times the frequency, and we all know that. Okay, normally like a wave V equals to F lambda. In this case, this V is going to be our speed of light, F times lambda. So my F here is going to now mean speed of light divided by the lambda. So what that means is that I can say my E equals to HC over lambda. Okay, and what that will mean is going to be 6.6 times 10 raised to the power minus 34 minus 34. That's what we have in the question. Minus 34 times 3 times 10 raised to the power 8, all divided by the lambda, that's the wavelength, is 700 nanometer. Of course, to say nanometer, if you look at 700 nn from the question, that's what we have. That is going to mean 700 times 10 raised to the power minus 9. If it's pico, that's going to be, if it's pico, If it's micro, you see micro, that's going to be 10 raised to power minus 6, and it goes on and on like that. So, but here you have 700 nanometer, and this is what we are going to, of course, compute. In computing this,